Welcome back. In the last video, we covered these first three examples of exponential equations and how to solve them. In this video, we're going to cover just three more examples, just real quick. Examples 4, 5, and 6. Of course, I know you can only see number 4 right now. 5 and 6 will appear momentarily. But let's start with number 4. Okay, we have 7 to the negative x power equals 21. Now, if you're going to try method 1 that we talked about last time, where you want to write these as the same base, well, the question that you got to ask yourself is, can I write 7 and 21 with the same base? And the answer is no, you can't. If you think about things with a base of 7, okay, or powers of 7, 7 to the first power is 7. 7 to the second power is 49, okay? And of course, those numbers are only going to get bigger, so 21, which would be somewhere in between them, is not going to fit. 21 would not have some base of 7. So we can't really use that method. We're going to have to use method 2, which talks about, where we put the logs on both sides. So let's try that. Let's put a log on both sides. Put log of 7 to the negative x power equals log 21. All right, now the whole reason we do that is for part of it's the convenience of moving this exponent. This exponent we're going to relocate to the front of this logarithm. It's a very convenient rule for us, so this becomes negative x times log of 7. So that's a very nice property that logarithms provide, is being able to move that exponent kind of out of the way. All right, and this equals log 21. Now, I want to try and get this x by itself. Notice I'm multiplying the log of 7 to this negative x. So what I'll do is I'll go ahead and divide by log of 7 because dividing is the opposite of multiplying. So we'll get negative x equal to log 21 divided by log 7. Let's use a calculator. Log 21, parenthesis, divided by log 7. Should be a decimal, yeah, 1.56. So we'll just kind of round it to that, 1.56. So if we want to get rid of this negative, the technical way of doing it is divided by negative 1. That removes that negative, leaving it just with x equal to, of course, negative 1.56. All right, so that's how I guess you would do number 4. And a lot of these are very kind of repetitive. Some of the same steps repeat over and over again. You put a log on both sides, you move the exponent to the front, you divide by a logarithm, and then you kind of just do your typical algebra. All right, let's try example 5. 9 to the 8 minus x equals 27, the x minus 3. This is tricky. This works pretty much, very differently, both methods, but both methods are equally as complicated, I guess you can put it that way. So if you're using method 1, you want to write these 9 and 27 with the same base. Can we write 9 and 27 with the same base? Well, if you go back to that list that we wrote down in the last video, you'll notice that powers of 3, 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, 9 and 27 both make that list. 9 can be written as a base of 3, and 27 can be written as a base of 3, which is exactly what we're going to do. So, there's the number 6. So 9 is the same as 3 squared, so we're going to change that to 3 squared, right? 8 minus x. And then equal to 27, which is what we're going to write as 3 to the third, to the x minus 3. All right, so now they both have the same base. We're going to combine. We have to, these exponents here, we have to multiply together. So 2 times 8 minus x, we kind of distribute. We'll get 3 to the 16th power, and then minus 2x power as well. So 16 minus 2x power. And then we'll do the same thing for the next one, is we'll distribute this 3 to multiply it to both x minus 3. So 3 times x would be 3x, and 3 times negative 3 would be negative 9. So we have 3 to the 16 minus 2x power, and 3 to the 3x minus 9. And if you're wondering where I got those exponents, remember it's because 2 times 8 minus x equals 16 minus 2x, and 3 times x minus 3 is 3x minus 9. So that's where this came from. if I didn't explain it well enough the first time. But now, if the bases are the same, that's implying, and they're equal to each other, that's implying that these exponents are also equal to each other. So, we'll write that equation. 16 minus 2x is equal to 3x minus 9. Okay, now we'll just solve using standard algebra. So let's move this x term over by adding 2x. You could move the 3x instead of the negative 2x, but it doesn't really matter. We'll get 16 left on the left side. 3 plus 2 is 5x, and then minus 9. So we'll add 9 to both sides. We'll get 25 equals 5x, and we'll divide by 5. And of course, x will equal 5. Alright. It's a pretty good way of doing it. I guess the most complicated part is the very first two steps, because once we get up to this point, everything after it's pretty standard. But the first two steps, takes a little bit of thinking. It's just cleverness. So being able to remember that you can write 9 and 27 with bases of 3, and then also making sure that you combine those exponents properly when you distributed them. Okay, but from that point on, it's regular algebra. But if you're going to use the method 2, I'll go ahead and do it that way as well, just so you can see it. Method 2 would be log 9 to 8 minus x equal to log 27 to the x minus 3. Again, every time we do this method, we're doing it so that we can move these exponents to the front and have this as 8 minus x. Now keep them in parentheses because they are a group, they go together, times log 9 equal to, and then we'll put x minus 3 in the front of log 27. So at this point I want to merge my logs together, so notice I'm multiplying them on both sides. If I want to move, like, let's say log 9, I'm going to divide it, since dividing is the opposite of multiplying by log 9. And that's what's going on here. So we'll just have 8 minus x on the left, and now let the calculator do log 27 divided by log 9. So log 27, close parentheses, divided by log 9. And we get 1.5. Now, in a lot of math classes, we're not typically used to seeing, I guess, this side written in this, direction or way of, I don't know, whichever one's coming first. Typically, this is the same thing as saying 1.5 times x minus 3, which if you saw it written this way, which is, like I said, just the reversal of how it's currently written, you would know that you'd be distributing this, which is exactly what we're going to do. But it's kind of like distributing backwards, I suppose. So we still have 8 minus x, but 1.5 times x would just be 1.5x. And then 1.5 times negative 3 is negative 4.5. So now I'm going to do a couple different things at once here. So I'm going to move this x over here. I'm going to do that by adding x. And I'm going to move the minus 4.5 to that side as well. So I'll do that by adding 4.5. So I'm going to do kind of 2 steps in one. That's okay. 4.5. So that's going to cancel out those. We'll have 1.5x plus 1x would be 2.5x. And 8 plus 4.5 would be 12.5. And then we'll divide by 2.5. And we'll get 5 equal to x. So it's the same thing. Of course, it's not going to be a different answer just because we solved it using a different method. But if you're going to use that method, that's how it would work. I just wanted to make sure I kind of showed it to you. All right. We have one more cover in this video, and then we'll end it. So 4 to the x minus 1 equals 5. Now, if you go back to that list, you'll quickly see, or maybe you might already know, that we can't write these as a common base. 5 can't be written as 4 to some power, or 4 can't be written any differently either. So we're going to have to use method 2, which just, like I said, it's my go-to method. When in doubt, use it. So put logs on both sides. Remember, this exponent, we're relocating x minus 1 times log 4 equals the log 5. And then divide by log 4. Alright, so we get x minus 1 equal to, I don't remember, so let me get the calculator again. Let's see here. What was it? Log 5 divided by, oops, not times, divided by log 4. And 1.16. Alright, we'll add 1 to both sides and we'll be done. We'll get x equal to 2.16. And there we have it. Alright, so again, I just wanted to show you those kind of two ways to solve exponential equations. Either change the base, get the bases to match, like we did in number 1, where we had changed 8 to 2 to the 3rd power, where we changed in number 3, we changed 27 to 3 to the 3rd power. Kind of like we did in 5, where we changed both 9 to 3 squared and 27 to 3 to the 3rd. Changing base helps. It makes things a little bit simpler. I guess in some people's opinions. But when in doubt, you can always use the log method. That's kind of, like I said, it's my go-to. It works every time. It's easy to follow because it's basic algebra steps, dividing, moving things around, kind of stuff like we did in Algebra 1. It reminds me of that a little bit. All right, I'll end it there, guys. We'll see you next time. We'll be solving logarithm equations instead of exponential equations. So you'll see kind of the similarities but yet differences on those. Okay? See you later.